Welcome to our NPTEL courses on the power quality improvement technique. Today is our third lectures on the multi-level inverter and its control strategy. Mainly we are discussing on the suitable PWM technique for this multi-level inverter. Now we were discussing the phase shifted PWM, and just for the recap I am discussing it. So, in case of the we have, please refer to my previous lecture. In the phase shift level shifted PWM, the triangular wave carriers are vertically shifted. In next slide I am going to show you the picture that the bands they occupies are contiguous. That means you will find that more compact. In an M level cascade H pitch inverter requires M minus 1. If you have a 5 level, you require 4 carrier, all having the same frequency and the amplitude. The amplitude modulation index is defined by MA Vm by Vcr M minus 1 for M is M 0 to 1 modulation index, and for the frequency modulation index remains the same that of the phase shifted modulation, that means MF by FCR by MM. So, you do not have any advantage on the frequency on the level shifted modulation. But what is the advantage of the level shifted modulation? It is very easy. You generate same triangular wave and add the DC shift to it, and thus you reproduce all these waveform. So, it just this is a same phase. So, it is red one, thereafter this is the upper triangle, this is the lower triangle, thereafter this blue one, then green one, then yellow one. In these schemes, the level shifted PWM, it can be in phase disposition. These are all in a same phase, or it can be phase opposition disposition. This can start 180 degree phase shifted. It is the same op amp, you just give it to the inverted logic. So, you can have a 180 degree phase shift. So, making this control logic is quite simpler. And another is phase opposition disposition, that is what I was talking about. Then it will start like this. So, instead of the, so ultimately this has to be, this point will come here for the phase opposition disposition. All carrier wave above 0 reference are in phase out in opposition with those of the above 0 phase reference. So, 180 degree phase shift will be there for this carrier wave and this carrier wave. And another is, that is what I was talking earlier, this alternative phase opposition disposition. So, this one is your ultimately this one, where this red and blue are in a, you can see that in the same phase, where this green and yellow are 180 degree phase shifted. And on the other hand, it is apod, this is more preferred. Here this one and this one are 180 degree phase shifted, and again, so this green and red are in the same phase, same for the blue and yellow are in the same phase, and it looks like quite compact. So, this apod. So, this figure shows that, pardon me, this cannot be shown properly. So, I will just, this figure, this one shows that the carrier wave with phase disposition, phase opposite disposition and alternate phase phase opposite disposition, this is the C. So, what happened if you have this level shifted, it is a 7 level cascade H bridge. So, you have a 6 such carrier wave. So, you have these values and you have 1 2 3 and 1 2 3, and you can see that these are the gate triggering for the first gate, second gate, third gate, and same way for the other, and ultimately this will be come into the picture when only upper carrier wave 1 is on. So, then only this will come, and ultimately this will come when it will be above it, and similarly. So, you get the logic for the other for this positive half cycle, ultimately you will get this kind of level 7 level in case of the cascade H bridge inverter. So, you can see that this is the 3 levels and rest is also 3 level. So, this is a way to work with the phase shifted level shifted PWM. The device switching frequency is obtained by multiplying the number of getting pulses per cycle by the frequency of the modulating wave. This is the way it works. This device switching frequency is not same, that is a one of the major drawback. If you go back, you can find that this switching is more, and for this reason we can see that in the different H bridge, cascade H bridge will operate at different frequencies, and if you put them in the same DC voltage bus, then the losses will be more to those which is switching more. Output voltage of this H bridge VH1 and VH2 and VH3 are all different as we have seen, and the level shifted PWM, the device switching frequency is not equal to the carrier frequency and it is different. Inverter switching frequency is equal to the carrier frequency, but individual frequency is generally more than the carrier frequency, switching frequency, and thus the average switching frequency is given by this switching frequency by m minus 1, and ultimately this is the case. So, for the level shifted one, please recall we have a phase shifted one also. The ratio we assume that 60, and for this reason we can see that this is the phase voltage versus Vd, and you have a fundamental, apart from that you have a 60th harmonic, and thereafter MF plus 6 and MF minus 6 and so on, and ultimately you get around 18% THD. On the same hand, assuming that MF is 60 for the 7 level, and for the line voltage you can find that these are the all spectrum. At 60 it is less, and but at MF, since it is 7 level, you will find that it is 8 will come into the dominant figure. So, you will have a component MF minus 16, MF minus 8, MF minus 2, plus and minus both. The inverter, that is what I say, the inverter phase voltage contain triplet harmonics such as MF and MF plus minus 6, with MF being a dominating harmonic, this one. But you can see that this is missing here in case of the line voltage. But the triplet harmonics are absent. So, and ultimately all this MF minus 6, this component goes out, and thus you get a better THD in line voltage. Few more observations. The conduction time of the of this device is not evenly distributed, as we have seen, and due to that what happened? The conduction losses of the different cascade H-bridge multi-level inverter cascade entities, cascade H-bridge will be different. So, losses are not equally placed. So, there will be a local hotspots. The switch device usage and average power handled by the each module is not evenly distributed. That is also a challenge. So, this is the something we have to address, and we have to find maybe the better control technique. It causes the current distortion at the input side. So, this is the major drawback while we from the power quality point of view. So, if you have been feeding, so input current distortion will occur. To evenly distribute the switching and the conduction losses, the switching pattern should rotate among all H bridge. So, you first give some kind of pattern triangle wave to some of the H bridge, then after few cycles you change those pattern, so that it will rotate evenly, so that these losses get distributed throughout those all the H bridge equally. This is the way we generally do it. Now, this is the case of the that which I was discussing right now, level shifted PWM, and this one is a modified level shifted PWM. Let us see what is the difference between these two. The problem of the uneven power distributions in level shifted PWM is solved by alternating level shifted carrier of each module. So, what does it do? The rotation of the levels are performed separately for positive and the negative carrier. So, what happened first, once you can see that after this will go up and this will come down. So, here and thereafter again this will go up and this will come down. I try to show the bolder portion of it. This is the bolder portion of it, this is the topmost carrier wave. So, it will come down, and this waveform which is little gray in color, that carrier wave will go up, and then again this will go up, and then it will go up, down, go up, go down, go up, go down, like that. So, it will have a Gothic kind of structures, and that will be the carrier wave 1, and this gray one will be the carrier wave 2. Same is repeated in the negative half cycle. This is the carrier wave 3, the gray one, and the dark one is the carrier wave 4. So, this will after this will go up, again come down, again go up, come down, like that, to equispace the losses, conduction as well as the switching. So, now there can be another solution to it. Instead of this require little complex circuitry, every quarter cycle you have to give a phase shift, sorry, you have to give a DC boost. So, ultimately what happen, it is quite easy. So, you have this one and you have a square wave. So, you add a square wave, it goes up, then again it comes down, then again goes up, then again comes down, like that. So, you have to add these 2 cycles. Okay. So, this is the way we generate the previous modified phase level shifted PWM. Now, this is a hybrid level shifted as well as the phase shifted PWM, and it is a combination of both. So, we always believe that hybridization works better. So, hybrid of the phase shift and the level shift PWM both. See that what we do, the carriers are subjected to the vertical as well as the horizontal shift. So, here this is a red line and this is easier to do. So, you can see that otherwise you can have only this and as well as the black portion of it and like that, but you have phase shifted it, the red one. Same for the black one, and thus its mirrored image, if you consider this x axis line to be a mirror, and this will be followed into the x axis. You just try it out different control technique, because unless you try those techniques here, you will not be able to appreciate this lecture. The average device switching frequency of the hybrid modulation is half of phase shifted PWM. Why? Because you can see that this is your switching frequency of the carrier wave, but effectively you are coming to this red and black as a effective carrier wave. Thus, the dominant harmonic are concentrated around n minus 1 by 2 into MF. So, this is the issues here. So, what we can conclude from the hybrid modulation asymmetric multi-level inverter, this technique involves both high frequency and the low frequency switching. The power modules are operated at a low frequency to reduce the switching losses. Power modules are controlled with the unipolar PWM, low power modules, and this method is only feasible if the decelerating voltage, if the decelerating voltage of the carrier wave and the modulating wave are the integral multiple of some small one, then only this is a feasible. This is another strategy. This one is called hybrid modulation asymmetric cascade H bridge multi-level inverter. In these techniques, you have a combinations of both high switching frequency and the low switching frequency. The power module operated at the low switching frequency, because you can have a combination of the maybe GTO IGBT. Some cascade H bridge made of GTO, some cascade H bridge made of IGBT. So, those who are made of GTO, they of course they can handle more amount of power, and they will operate at the low switching frequency to reduce the switching losses. And lower power module is controlled by this is the unipolar PWM, and this method is only feasible if decelerating voltage of the higher power module are integral multiple of the small one. So, you generate this amount of thing, then what you do, you add or subtract this thing. So, thus you can get a multi-level kind of thing. This is the way it operates, and for the module inverter V3 is less than this, and where to make this condition for fulfilled, that is V3 should be greater than V2 and greater than V1. Now, you see that the hybrid modulation technique, this is the one control cell, and ultimately you generate the voltage V3 and it will come out here. So, this one will be fed here. This is another control cell, then this will be feeding here. Ultimately, you will get a value VAN. Here if there are 3 power module, the threshold voltage, that is H plus equal to V 1 plus V 2 and H 2 will be equal to V 1, and combination of it will give you the different level of voltage. This is the way of hybrid modulation technique. So, see that how does it work. This is the low frequency device, maybe GTO. So, it will be on for most of the time. With that you can have this kind of carrier wave, and thus you have a switching like this. So, ultimately you subtract this is V minus V 3, and so you got V 2 minus V 3, and then again this V 1 will be V 2 minus V 2, and ultimately what you get essentially is that V 1, V 2, V 3. This is all you see that how to reduce the THT of this output waveform for the inverter. It is not that you will generate it, and you can generate almost close to the sine wave, and that can be feed it to the motor. Thus, what we can conclude here is that the total output voltage VAN equal to VA plus VA2 plus VA3, and hybrid modulation has not uniform power dissipations among these devices, because you can see that this is most of the time is on, and it may be IGBT, it may be GTO, and others are IGBT. So, losses also will be spread over differently. This is also a challenge, but this voltage are less than this voltage. So, for this reason it works. See this, you can see the voltage here is a per unit value 1, and it is restricted to 0.5 almost, and here it is restricted to very close to 0.2, 20% of the voltage. And that switching, because here switching is more, and you can have a faster device with the higher switching frequency, and thus you can get this kind of close to sine waveform. Now, let us come to the space vector modulation technique. I have discussed the space vector modulation technique for this 2-level inverter, and that has been extended to the 3-level inverter. So, basic assumption is same. So, we require to find it out, and since there was a, we managed with 1 and 0 in case of the 2-level, but we require to, since there is a 3-level, we shall state the concept P for the positive, 0 or O for the middle level, and the N for the lower level. So, this is our convention we are following. We have taken this convention from the Benhu books. The operation of the each inverter fetch leg can be represented by the 3 switching states, that is P0, PO, Pn. Taking all these phases into the account, the inverters has a total 3 to the power 3, that 27 states, possible combinations of switching states. Among 27 switching states, 8 states are redundant. So, total 19 vectors are possible. To find the relationship between this switching states and their corresponding space voltage vectors, the same procedures as used for the 2-level inverter. Let us come for the grouping of these vectors. Based on the magnitude of the voltage vector can be divided into the 4 groups. One is 0 vector, you know that 0 0 0 or plus plus plus, sorry, it is in this case 0 0 0 or 1 1 1 are the null vectors, or here you can have a 0 vector. So, 0 vector will be a switching states of PPP, that corresponds to 1 1 1, but here also there is another extra thing that was not present in case of the 2 level inverter, that is OOO, and also because then also you can get 0, N and N, all the lower switches are closed, and the magnitude output voltage is going to be 0 then. The small vector V1 to V6 all having a magnitude VDC by 3, each small vector has 2 switching states, one containing P and the other containing N, and therefore, can be further be classified as P or N type, or some books write triple plus and triple minus type small vectors. So, there will be a medium vectors, these are, we will say that it will be, these vectors are in between V7 to V12 and whose magnitude is 3 VDC by 3, and ultimately it is VDC, and there will be a large vector. So, that will be the full length of this A. So, that will be 2 VDC by 3. So, there will be VDC by 3, there will be VDC essentially and 2 VDC by 3. So, this is the case. Now, see that I just represent it here diet clamp 3 level inverter. For sake of simplicity, you can extend it to this any level. So, this is the 0, and so you can have this PPP N and N 0 0 0 as a 0 vector. Thereafter, V1, this is the magnitude. Look, this magnitude is essentially 2 V by 3, and this magnitude is essentially, you can have a half voltage vector, you can see the magnitude of it. So, from the triangle you can see that this angle value. So, that magnitude is essentially the radius, and radius is your, essentially it is radius, and that radius value is your VDC, and this much magnitude will be for the 2 VDC. This is some, this is called, these vectors are called half angle vectors, and this is called the half voltage or the small vectors in some notations. So, what happen here? So, you will have this hexagonal structures. So, now how you will calculate the timing of this hexagonal. Now, if you are here, then you know that what are the voltage you will be made of. See that it is 0 0 0. Now, there is a redundancy, that is a beautiful part of it. If you are at O or 0 0 0 whatever you say, then if you want to apply the V1, then you have option to apply POO and ONN. Generally, since it is a 1, if you are 0 0 0, then it makes sense to have a 1 bit change and come to POO. But let us say if you are N and N, that is also the case. So, if you want to apply V1, then you should apply O N N N. So, we want that 1 bit change to have a, so that switching losses will be also minimized. If you have a 2 bit change, that means the more switching on and off. So, thus there is a combination. So, you can generate the voltage V1 with the help of POO and ANN, and once you if you want to generate this voltage, the full voltage vector, that is essentially your PNN. Same way the negative vectors, that will be NPP. Similarly, it will be PPN, it will be NPN, it will be NNP, and it will be PN. So, these are the constant vectors. Apart from, and these also are constant vector. If you want to generate the voltage vector 7, this is half angle vector, this angle is 30 degree. So, PON is the only option, but if you want to apply the half vectors, for example, here you can have option, you can choose for PPO and OON. So, thus you can see that in this region what are the vectors will be useful to construct this waveform. So, please go back, since this it is restricted here, and take those portion of the triangle, and what are the vectors will be useful to construct these devices. So, let us consider that it is in this coordinate, first coordinate. So, ultimately you make with these vectors V1, V3 and V2. So, how you will calculate the timing of these vectors? So, now this is a way to be followed. Dual time calculation of the neutral point clamp inverter is also based on the volt balancing principle, as we have seen and detailed discussion for the 2 level inverter. The reference vector Vref can be synthesized with the 3 nearest stationary vectors. Here you can see that it is V1, V2 and the V7, and thus you just write it down, V1 into TA, let us for it will be on, that is V2 into TB plus V7 into TC, and that should be equal to Vref into TS, and TA plus TB plus TC should be equal to TS, where TA, TB, TC are the dual time for the V1, V2, V7 respectively. And thus what happened, these are the options. So, if you have switched PPP, all the upper switches closed, it means that you have Vz no effect and 0 voltage vector. Okay. So, you short all the legs. Same way, if you have P00 or POO, then what happen? Only one vector gets the voltage, others are shorted. So, you got a small vector. Similarly, if you have, you can see that this combination, this is the n-type small vectors, that is ONN. So, you can get the same voltage. Similarly, PON, Vz is not defined and it is a medium vector, and PNN, and it is a large vector. So, in that way we can using these vectors, and by using the redundancy state, neutral point voltage deviations can be minimized and you can have a redundancy and thus got a more reliability into the system. Thank you for your attention. I just complete your multi-level inverter and its PWM technique for it, and that will help you to reduce the drive application mainly, as well as when you connect to the UPQC or the shunt active power filter, this kind of techniques are used to mitigate the voltage and the current harmonic. Thank you.